the next part of the course, which is the study of algorithms. So really, we've been studying algorithms all along. So anytime you are presented with a problem and you express the solution to that problem in code, then somewhere in that process you've developed an algorithm. So what's an algorithm? It's just a precise list of instructions that solves some problem. So you can express algorithms in code, which is what we've mostly been doing. You can also express algorithms just as text. You can express them verbally or through in written form, in plain English text, or there's sometimes pseudocode, which is a kind of code that's a little bit easier, more like English than actual code, but doesn't execute. So they're this sort of nebulous thing which basically expresses a well-defined sequence of steps that you perform, and if you perform these things, some problem gets solved. So, in other languages, if someone says, okay, how do you add up all of the elements in an array? So how do you compute the sum of an array? Well, you might say, well, first I make a counter and I set it equal to 0, and then I iterate through the array one element at a time, and then I add that thing to the counter. So that's a description of an algorithm right there. It's a plain language description, and you can implement that in code. That's another way of describing the same algorithm. So we've already been doing this, and now it's time maybe to do it a little bit more formally and to talk about some properties of algorithms. So until now, we haven't been super concerned, with the exception of one assignment, we haven't really been concerned about the efficiency of algorithms, except for assignment, I don't know what it was, 5 maybe, where we saw that if you use sets and dictionaries appropriately, some things can run a lot faster. Now we want to start looking at the finer details, including performance of algorithms. And just before I continue, so I remember, today is Memorial Day. So at about 11 o'clock, I'm going to stop for a minute, and I'll be silent for a minute. You can do whatever you want in that time as long as it's silent. So reflect on the meaning of Memorial Day. But just be quiet for a minute. It won't hurt me to be quiet, and it won't hurt you either. Okay, so before we can really study algorithms, there's a closely related thing that many of you know about, but I want to make sure we all understand it reasonably well before we continue, and that's the notion of recursion. So there was an example of recursion on the exam. I think it was, I don't know, maybe for computing, for printing something. And I think many of you understood it. And in class, in fact, in the earlier classes, often when I would ask a question, you would give me a recursive solution for it. But I want to make sure we all understand it, and we all understand it well, because it's fairly important for studying lots of algorithms. So here I'm going to write a recursive function. I'll call it printer. It takes one argument, which is an integer n, and it does the following. If n is equal to, well, let's do it this way. We'll print n, and then if n is equal to 0, we'll just return, and otherwise we'll call printer of n minus 1. Okay. So it takes this integer argument n, it prints it. If it's equal to 0, it returns, and otherwise it prints, it calls printer of n minus 1, and then implicitly we'll make it explicit just so we can see what's happening. Then it also returns Functions just return automatically when their definition ends, but we can do that explicitly if we want. Okay, so what happens if I call printer of 10? Yep.
10 all the way down to 0 each on the line.
Okay, so it'll print 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, each one on a new line because that's what print statements do. They put a new line after they're printed unless you have a comma, and that's it. So there you go, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so is that clear how that works for everyone? Right, so we print n, and then we recursively do the same thing on n minus 1. And this only stops when we get down to 0, in which case we return immediately without recursively calling this thing. Okay. Now, if I take this print statement and I move it there, what happens? Yeah. Yeah. So in that case, it'll return, if n is 0, it'll return before printing anything. So the end result is that it doesn't print that final value 0. Okay. So to really know what's going on, and maybe we'll say printer of 5 here. So it seems like you understand what's happening, but I would like to really look at the details of the nitty-gritty of how all this is implemented, because we'll need to know it for some of the other examples we're studying. So anytime you call a function in Python, there's this thing called the stack. And it's called a stack because it is a lot like a stack of, let's say, plates in a restaurant, where you put plates on top of the stack and you take plates off of the stack, or in your cupboard. And so there's basically one end of this thing, of this stack, where all the action happens at. It's called the top of the stack. And then deeper down, you don't get to the deeper down plates unless you've removed a lot of the upper ones. And so every time you call a function in Python, it creates this thing called a stack frame. And you can think of it as one of these plates. So it goes on top of the stack. And stack frames have a bunch of stuff in them. And the main thing they're responsible for is the variables and parameters to the function that created them. So for example, when I call printer of 5, what happens is a new stack frame gets created. And printer only has one variable. It's actually this parameter here, n. And so it gets created with this parameter, this variable called n. And since I called printer of 5, n gets assigned the value 5. Okay. Now, anytime you reference a value or a variable in a function, it looks for it in the current stack frame. So in this case, for example, when we check if n equals 0, what we're really asking is this variable here, is that thing equal to 0? It's not, it's equal to 5. So we move to the next line and we print the value of n. So that's when we print the value of 5. And then we compute the value n minus 1, and we call printer on that value. So we're calling a function here, so that makes a stack frame, which has its own things. So this actually creates another stack frame. that has this variable n in it that gets assigned the value 4. Okay. So for whatever reason, when we draw stacks in computer science, we typically draw them growing downwards, even though that doesn't really make as much sense as this plate example. So it's more like a stack of magnets that are hanging upside down. So this thing is the top of the stack. And now, well, we're calling printer again, and we start executing this this function. Is n equal to 0? No, n is equal to 4. So we'll print n, and then we'll call printer of n minus 1, which is going to create a new stack frame with n equals 3. So while this recursive function is executing, there are a whole bunch of different variables. They're all called n, and they all have different values. The one that's being referenced is the one that's on the top of the stack. It's the one for this, this record here. So then this does the same thing for n equals 2. And then n equals 1. And then finally, n equals 0. And when n equals 0, the function actually returns right here before doing anything else. And so if we call a function if a stack frame appears when we call a function, then when we return from that function, the stack frame disappears. So after we return from this function call, this stack frame disappears. It gets wiped off the stack, and now this is the top of the stack. Now, one thing that's a little bit less obvious is the stack frames, they keep track of a few things. They keep track of the parameters to the function. They keep track of the local variables. But they also keep track of where the function is executing. So what line of the function is executing, or what piece of code in the function is executing. And so in this stack frame here, when with n equals 1, well, we called this thing with n equals 0 at this point. And so the next line of code that we're going to execute is this return statement here. So it's just going to return. And so these things all get popped off the stack. And eventually the last one gets popped off the stack, and that's when we get our control back to the prompt here. Okay. All right. Are there any questions about that? Yep.
What's the maximum? Because I tried 50 squared, it says recursion.
So the maximum, at least in the implementation of Python that's on my machine, is about 1,000. A little bit less, in fact. So I get an error if I try and call printer with 1,000. And we can see where it stopped. There it is. It gets all the way down to 2. So it's like 998 was okay, but 999 was too much. Yeah.
You call it a stack frame. Is it like it contains fields? So there's multiple fields within that record, like almost?
Well, for us, we just think of it as this big box that contains variables and parameters. So, and so yeah. So this big box here is the frame. It contains this parameter n in this case, but it could contain other local variables and so on. Okay. So that's clear. All right. So if we change this code slightly, and we put the print statement there, after the recursive call. what will happen? Yeah.
Will you return the final value?
Well, this function doesn't actually return anything ever.
Will you return the final value?
Let's see. So one suggestion is that it will only print the final value. What's the final value? 0. So let's think about that for a bit, see if that's possible. So printer of n, does it, so when does it not print anything? Yeah. So it doesn't print anything when n equals 0. So if I call printer of 5, for example, will it print 5 eventually? Yeah, because 5 is not equal to 0. It'll call printer of n minus 1. That'll do whatever it does. And then it'll print 5. Right? So, okay, so it seems, and when it calls, printer of 5 calls printer of 4 here, and so printer of 4 will eventually, 4 is not equal to 0, so printer of 4 will eventually print 4. And so so everything is going to get printed, but what's different about this? Yep. Backwards from the way it was going before, which was backwards, so upwards. Yeah, right? Because if we think about this, we call printer of 5. 5 is not equal to 0. It'll call printer of 4, and that'll do something. We can guess what that's going to do, but even if we don't want to guess, it'll do some stuff. And then it'll print 5. So the last thing that gets printed will be 5. And now we can just reason inductively about this and say, well, when it calls printer of 4, then the last thing that will get printed will be 4. So 4 will be printed just before 5, and then 3 will be printed just before 4, and so on. And so let's try it. So indeed, it prints 1, 2, 3, 4, 5, rather than 5, 4, 3, 2, 1. Okay? And what if I put in both print statements? Yep. Yeah. So you call printer of 5, it will print 5, and then it'll call printer of 4, which does whatever it does, and then it will print 5. So that means whatever gets printed is going to start with a 5, and it's going to end with a 5. And now what goes in between that is whatever happens when you call printer of 4, but by the same reasoning, that thing is going to start with a 4 and end with a 4, and the thing inside of that is going to start with a 3 and end with a 3, and so on. And so what we get is this palindrome. Oh, I forgot to reload. Is this palindrome that counts down 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. Okay. So the stack frame picture looks exactly the same. It's just that for all of these things, it's just that when the printing happens depends on where the print statement is. So, for the first print statement, that happens up here. We'll print 5 before the stack frame for 4 appears, and then we'll call printer of 4. We'll print 4. Then we'll call print 3, print 2, print 1. We don't print 0. And then on the way back up, as each of these things returns, then the print statement that comes after that is executed. Okay. So is that clear? Okay. All right. So now, everybody remember what factorial of n is 1 times 2 times 3 times 4 times all the way up to n. So how could we write that recursively? Yep. So return factorial of n minus 1, like that. Okay, so we'll go with the base case. So factorial, if you look in a math textbook, it's defined for, even for n equals 0, and its value is 1. So if n is 0, we'll return 1. And otherwise, we return factorial of n minus 1. Is that right? Yeah, so if we just do that, then, okay, so we get factorial of 1 is 1, factorial of 2 is 1, factorial of 3 is 1, factorial of 4 is 1, and so on. And that's because, well, if we look at this stack frame picture, we compute factorial of 2, that creates a stack frame with n equals 2. That calls factorial of 1, creates a stack frame with n equals 1. That calls factorial of 0 with a stack frame with n equals 0. And what happens when n equals 0? Well, when n equals 0, we return 1. So this stack frame disappears, and when it does, it returns the value 1. Now, what happens after that? Well, now we're in this stack frame here where we called factorial of 0, and this just says, well, we should just return whatever value that returned. So that returns 1. And this, now we're in the stack frame where n equals 2, but the code says just return whatever factorial of 1 gave us, and so we return 1. So that doesn't work. Instead, what we want to notice is that this thing here, so another way to write this factorial is to include the second last thing, n minus 1, like this. And now notice that this part here, this is the factorial of n minus 1, right? 1, 2, 3, 4, 5, all the way up to n minus 1. That's the definition of the factorial of n minus 1. And then to get factorial of n, we have to multiply that thing by n. So we really want n times the factorial of n minus 1. 1, 2, 6, 24, 120, and we can even do factorial of 100, and we get a really big number. Okay, so there's a recursive definition of factorial. Now, so one thing I'd like to point out is we're just learning now, and so we're doing some simple examples, and these are not good examples of recursion because we could have done these things without recursion, and because we've used recursion, we've actually made functions that don't work for large inputs. So for example, factorial of n won't work for n equals 1,000. We'll run into this problem with the recursion depth. And that's just because this picture here of these stack frames, which are growing down, 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 well, they're growing down 1,000 times. And at some point, Python decides that, well, it actually doesn't want to have that many stack frames. Each one of these things is taking up some amount of memory. So if this thing goes on indefinitely, then eventually we'll use up all the memory in the computer, then we'll start going to the hard disk, we'll be using all that up, and the whole system will slow down just because we're using all of this memory. And the fact that the recursion depth is 1,000 is somehow a clue to Python that maybe somebody made a mistake in their program. In this case, it's not a mistake. We really meant to do it that way, but it's not a good way of doing it, and Python thinks this must be a mistake. I'm just going to stop this here, and what I'm going to do is return I'm going to throw an exception. In this case, it's a runtime error. Okay. So these kinds of things where you don't need recursion, right? We could write printer of n, that's just a for loop. We could count using a for loop from the range n equals 1 to, or I equals 1 to n, print I, and then for the range, or the other way around, for I equals n down to 1, and then 1 up to n, we could print I. We didn't need recursion there. And factorial also, you guys know how to do this with a for loop. Well, we've seen several ways of doing this. So these are not great examples. They're not things you would want to do in a real program, but they're just here to help us learn. And so in that vein, I want to write look at something a little more sophisticated, or a little more subtle. And I want to write a function which computes the sum of the elements in an array A, or a list A. Now, we know a bunch of ways to do this. The easiest way is just to say something like this. There's a built-in function in Python that does this already, so not terribly interesting to do it that way. I want to do it recursively. So what's a recursive way of adding up the elements in a list? No ideas? Yep.
I guess you could remove the last element away and put it in something else and then call the function again.
Okay. So the suggestion is we remove the last element and then we call the function again on what remains. So let's maybe think about that another way. So one way to think of recursion is as a way of delegating problems to someone else. So for example, I have a big list of numbers that I want to add up, and I say to someone, okay, you add up all of the numbers except for the first one, give me the result, and then I'll add that last one in. Okay? So that's really what we want to do, or you add up all the numbers except the last one, tell me what they add up to, and then I'll add the last one in. So the way to implement that in code is to say what we'll do is we'll return A at 0 plus summer of the rest of the array. So we take the first element and we add it to whatever the sum of the rest of the array is. Okay. Is this code good? Does this work? Is there anything missing? Yep. Yeah. So what happens when we get to the last element? Or, so more importantly, what happens if A does not have an element at position 1, or even an element at position 0? Right? This will give us an indexing error. If A is an empty list, then A at 0 is an error, and if A is a list of length 1, then A at 1 will give us an error. And so we can We can just try that. So A is the array 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We call summer of A, and we get an error which says list index is out of range. And indeed, that's because, and we get this big long trace like this of, it says the code that's executing right now is in this function summer. That code was called by this function summer, which was called by this function summer, which was called by this function summer, and so on, right up to the top, which was eventually called from the interactive prompt, standard in. And so we need to handle the case where the array is empty. And so the sum of an empty array is just 0, right? So if the array is empty, its sum is 0. Otherwise, we take the 0th element and we add the slice starting at position 1 and going to the end. Yep.
Don't we have to add, like, if the negative A is 1, just return the...
Well, let's check what happens. That depends exactly on how slicing works. But if we say, here's an array A of length 1. So A at 0 is definitely there. And what about this slice A at 1 to the end? That just gives us an empty array. So we're safe. This is a safe operation, even if A has length 1. So. Okay, can anybody tell me what the answer should be? Yep. 45. How did you get that? Okay. So, so there's a cute formula for these kinds of sums, right? This is the sum 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a cute formula and story for these things. I won't explain it here, but apparently Gauss, the famous mathematician, was able to do sums like this, but he was able to actually do this one. So from 1 up to 100. And he did that in a few seconds with a slate board, not with a computer, because there didn't exist computers then. So there's a cute formula for it and a story that goes with it, but you'll learn that in a later course. But there you go. So now we can compute this this sum recursively. Now, if we think about this thing, there's one bothersome aspect of this function, this summer function, and that's I'll leave that out for now. I'll ignore that for now. It's not the most efficient function. So for one thing, in order to copy an array, in order to sum an array of length n, it takes the first element and then it copies all the elements of that array into an array of length n minus 1, which then copies all of those into an array of length n minus 2 and into an array of length n minus 3 and so on, which is not a great strategy. When we look a little bit more at algorithm performance, we'll see exactly what that means. But even ignoring that, there's still another problem with this thing. So I can make A be a range of 500. Summer of A works then. I can make A be a range of 5,000. And then summer of A stops working. And again, that's because we get this recursive stack, which repeatedly calls itself. It tries to do it 5,000 times, but after about 998 times, Python says, hey, I'm not going to let this keep going this long. I'm going to cut this off and generate a runtime error. Okay. So basically, the picture that we get is essentially this picture here, except instead of these things being numbers like this, they're arrays, and these are the lengths of the arrays. So we start with an array of length 5,000, then we get an array of length 4,999, 4,998. This goes on nearly 1,000 times before Python says, okay, stop, this isn't okay anymore. So then the question is there a way to write this recursively where maybe it might actually work? So is there another way to think of doing recursion to add up all the numbers in an array? So already the first suggestion was a little bit different than this. The first suggestion was to write some function that looks like this instead. We take the last element, and then we add everything up to but not including the last element. So that's another way of doing it. So we can either take the first element and then add it to whatever the sum of the rest is, or we can take the last element and add it to the first n-1 elements. Is there any other ways we could do it? No? Well, there's lots of faster ways, but I'm thinking just about different ways of expressing this recursively. It seems a little, this way seems a little bit unfair. This is the equivalent of me saying, there's two of us here, and we have to add up this big list of numbers, and I say, okay, you go off and you add up all the numbers except the first one, and once you're done, I'll add the first one onto that. Now that doesn't seem terribly fair, does it? That leaves a lot of work for you, very little work for me. Yep? Well, this is almost the same as the factorial recursion, right? This says, the factorial function says to compute n factorial, I first compute n-1 factorial, and then I multiply by n. This says to compute the sum of an array of length n, I first compute the sum of an array of length n-1, and then I add this thing in. But if you think of two people doing this, what's a more fair way to do it? Yep. Yeah. So maybe a slightly more balanced way to do it, and we'll be careful. We'll have a couple of base cases. Make sure we handle everything. So if the length of A is 0, the sum is still 0. And if the length of A is 1, then the sum is just the value of that one element. But after that, we can do something like, say, let's compute the middle of the array. We'll call that M, the middle index of the array. And say, what I want to return is the array from 0 up to m. So that looks like this. So that's the first half of the array. And then I want to compute the sum of the second half of the array, which is starting at index m and going to the end. Okay? So that seems a bit more fair. If this is the work that I have to do the first half. You have to do the second half. This is about as even as it can be, and if the length of the array is even, we're both doing exactly the same amount of work. If the length of the array is odd, then I get to do a little bit less work because I'll get the shorter version of this. But that's okay because I'm the boss. And so let's check to see if that works. So A is range 10. Summer, let's check all our functions. Summer of A is 45. Summer 2 of A is 45. And summer 3 of A is 45. And we saw that summer of A, if I change the length of A and make it bigger, maybe 5,000, then the built-in sum function has no problem with that. The result is not that big. But summer of A crashes because it tries to make a stack of 5,000 things. Summer 2 of A, well, it crashes because it basically tries to do the same thing but adding from the other end. Now how about summer 3 of A? Yep. So who thinks it's going to crash? Right. Who thinks it's not going to crash? Okay, so I don't like this ambivalence. So put up your hand. So you choose now, one way or the other. Is it going to crash? Okay. Is it not going to crash? Okay, so it's about 50-50. So, that's why. Now who thinks it's going to crash? So one thing about when you're writing recursive functions and you're doing several different versions, this happens frequently that you call the wrong version. But this is now one function that just calls it itself. Okay, so summer 3 of A, it works. Summer of A still doesn't work. Summer 2 of A still doesn't work. Now, can anyone explain to me why that works and the other two don't? Yep. Okay. So if we look back to this stack diagram, and this is going to become really important when we start analyzing algorithms. If we look at what happens when we call, let's do a really, I don't want to draw 5,000 stack frames, but maybe 8 is a reasonable number. So look at what happens when you call, let's say, summer of A, the original recursive one that just takes off one thing each time. So originally, on the first call, A is an array of length 8. So you have A, and A contains 0, 1, 2, all the way up to 7. So that's the initial call. And in terms of box diagrams, you know, A is a variable, and it points to an array of length 8. Then, well, the length of that array, A, let's look at the code. It's not equal to 0, and it's not equal to 1. It's equal to 8. So that means it recursively calls it on an array which contains 1, 2, 3, up to 7. Now this is an array of length 7, which is not 0 or 1, so that makes a recursive call, which calls it on an array that contains 2, 3, 4, up to 7. That makes a call which contains 3, 4, up to 7. And eventually, this happens a few more times. You get an array of length 2, which contains 6 and 7. And then finally, an array of length 1, which contains only 7. And for this array of length 1, the code says all you have to do is return. So just return the value in this array. And so this thing here returns 7. This thing here returns 6 plus 7. Eventually this one before this one here will return 3, 4, 5, up to 7. This one returns 2, 3, 4, 5, up to 7. And eventually this thing returns 28. Okay? And if I gave it an array of length 5,000, the picture looks exactly the same, but there's 5,000 of these boxes all stacked up on top of each other. So now let's look at summer 2. What does it do? So this is summer. Sorry, summer 3 of A. Yep. You had a question?
Didn't you just do summer 2 of A? You got the 1 and then return 8, 0, which is only something that happens in summer 3.
Sorry, this one even goes down to 0. Yeah, so this one even goes down to, you're right, to an empty array, so an array of length 0, and then it returns 0. Yeah. Okay. But that doesn't all fit on the screen, unfortunately. All right. So summer 3 of A, we call it with this array of length 8 as before. So contains 0 up to 7. And what does it do? Well, it's not an array of length 0, it's not an array of length 1, so it computes the midpoint. So 8 divided by 2 is 4. So then it computes, it calls summer with the array that contains elements at position 0, 1, 2, and 3. Okay. So that calls summer again, and the elements are at positions 0, 1, 2, and 3. Okay. So now what happens? When you call summer with an array of length 4, what does it do? Or summer 3 with an array of length 4, what does it do? What's that? No, not yet. So first we've called this thing recursively. And what will that do? It will check if the array is of length 0. It's not. It's of length 4. It will check if it's of length 1. It's not. It's of length 4. It'll take 4 and divide it by 2. That's 2. And then it'll call this thing for an array of length 2. So it'll call summer 3, and the contents will be the first half of the array. Now that's being called on an array of length 2, and so it'll call it with the contents being just one element, 0. So now this thing is going to return, and what's going to happen after that? So I will give you 1 minute or so to think about what happens next. And do it quietly, please. Okay, so so here we are, we're looking at the operation of summer 3, and we've determined that if it starts with an array of length 8, it then calls itself an array of length 4, an array of length 2, an array of length 1, and the code says, well, if the length of the array is 1, we're done, we return. So that returns, and it returns the value a at 0. So in this case, it returns a 0. Now, when we return from a function, we take this thing, we take the stack frame that that function created off of the stack. So the first thing we should notice here is summer 3 so far only ever made 1, 2, 3, 4 stack frames. And now it's back down to 3 stack frames only. Summer, the regular summer, actually made 1, 2, 3, 4, 5, actually 9 stack frames before it started returning them. So somehow summer 3 doesn't have that many stack frames on the stack at once, and seems like it will be significantly less. So then this thing returns 0. And remember, stack frames remember exactly where the code was executing, and they pick up where that left off. So the code that was executing was this call to summer 3 with the first half of the array. So now it's going to pick up and make this second call on the second half of the array. So this is going to call summer 3 with an array whose length is 1 again, but this is the array that contains the value 1, not the array that contains the value 0. And then that's immediately going to return the value 1. Now we're back up in this stack frame, which has just called this and this. And now all it has to do is add those two results together and return the result. So it takes the 0 and the 1, adds them together, that gives a 1, and it returns the result. And when it returns, that means its stack frame is gone. Okay. So now what happens? Yeah. So now we're back up to this thing executing. It has just called this function, and it's returned. So now the next step is for it to call it on the second half of the array. So it's going to call it on an array A, which has 2 values, 2 and 3. That's going to recursively call. So if we look at what's on the stack right now, there's only 3 things on the stack. This, this, and this. So this is the top of the stack, this is the bottom of the stack up here, and there's only 3 things. And this is going to recursively call for the first half of the array, which is going to give a stack frame that contains only 2. Then it's going to recursively call it for the second half of the array, which is going to give a stack frame that contains only 3. The first call will have returned 2. The second call will have returned 3. It'll add those 2 things together and return 5. This thing now has called both of its functions recursively for the first half and the second half, 1 and 5. It adds those together and returns 6. And now up at the top, this thing is going to call its second, it's going to make its second recursive call, and that's going to be to the array that contains 4, 5, 6, 7. Okay. And now the rest of the picture is going to look like this. I won't draw in all the values. It'll call this. This will call 2 things. this we'll call this, and eventually everything will come out, and out pops the value of 28. Okay, so if you look at this, the way this whole thing executed, there were never more, at any time, there were never more than 1, 2, 3, 4 elements on the stack. 4 stack frames. Whereas over here, there were, up to 9 stack frames. So, why the number 4 over here? So what's special about the number 4? What's that? It's half of the length of this, but that's not quite. In general, it's going to be much better than half. Yeah. Yeah. So 4, it turns out, is log base 2 of 8 plus 1. Okay. So log base 2 of 8 is 3. And then there's just an extra 1 for this first stack frame that started out up here. So that's why this is 4. On the other hand, this thing is 9 because it's just 8 plus 1. Okay. So how many of you have seen logarithms before? Okay. So what is the log of 16? Log base 2 of 16? 4. What's the log base 2 of 32? 5. So what's the log base 2 of, let's say, 5,000 approximately? It's about 13. So it's some number between, I think it'll be between 12 and 13, which means that when I call this thing, so, if I call this thing with an array of length 5,000, I basically get the same picture here. 5,000 gets split into 2 arrays, each one of size 2,500. Those each get split into 2 arrays, each of size 1,250. Each of those gets split into 2 arrays, whatever. But the depth of this thing is only the number of times I can divide 5,000 by 2 before I get something that's less than or equal to 1. And that's almost exactly the definition of the log base 2 of 5,000, right? So the definition of the log base 2 is, if you're happy with plus or minus 1, it's the number of times I can divide this number by 2 before I get something that's smaller than or equal to 1. Okay. So all that to say that summer 3, when you call it on an array of length 5,000, yes, it makes the recursive stack gets bigger and bigger, but only up to depth about 13. Summer 1, or just summer, when you call it on an array of length 5,000, if it could, it would make a recursive stack of length 5,001, but it can't, so it crashes well before that happens. And in fact, summer 3 will have no problems even with an array of length 1,000,000. So it happily computes the sum of 1,000,000, an array of length 1,000,000. So, and that's because log base 2 of 1,000,000 is about what? It's about 20. So if you call it on an array of length 1,000,000, you get a recursive stack which is only of height about 20. That's much less than the limit, which is close to 1,000. So it's very happy to do that. In fact, it would happily do it for an array of length 1 billion, 100 billion, 1,000 billion, no problems there. You'd only get a recursive stack of somewhere in the 30s. Okay, so there's the advanced view of recursion, and this thing here, this recursive stack and this thing here It's called a recursion tree. We use it frequently to understand recursive algorithms. We'll draw these kinds of trees that explain what's happening at each phase of the recursion. But the key point is if you can draw your recursion tree for your algorithm, then one of the defining factors is the height of the tree, and that tells you how big of a stack that you will need. So if the height gets really big, if the height gets over 1,000, then you're probably going to crash. But if you can keep the height small, then you're good to go. Okay. So that's good. Here's another example of recursion. So again, this is still, I would still like to point out that this is a dumb example. So you wouldn't want to do code like this. You wouldn't want to write code like this, nor like this, nor like this. So those are all really bad examples because they can't solve big problems. They'll crash before they solve a big problem. This is a less dumb, but still pretty dumb example. You wouldn't write code like this. Well, for one thing, we'll see that it's not super efficient. It's slower than it needs to be. So there's that. But also because you could write this non-recursively in a much simpler way. And so now we're going to look at a good example. And that example comes from sorting. So has anybody ever heard of the quicksort algorithm before? Yeah. So how does the quicksort algorithm work? It wants to sort an array that contains a bunch of elements. So what does it do? It's a recursive algorithm. So what's the easy case for sorting an array? So what's the base case, the case that's really easy where we don't have to do any work? It's already sorted. That takes too long to check. Yeah. Yeah. So if the length of the array is less than or equal to 1, then that means it's empty, in which case there's nothing to do, or it only has one element, in which case it's definitely in sorted order. There's nothing that could be wrong. So we just return the input array in that case. Otherwise, the length of the array is bigger than or equal to 1. So for anybody who knows quicksort, what does it do at that point? Yep.
Does it take the average of the array and then...
Well, does it take the average of the array? It's not exactly the average, but in some sense, it's kind of like the average. So what it does is it takes a random element from the array. So if you pick a random one, that's kind of like picking an average one, maybe. So I'll need to import random. So pick one random element from the array. And now it wants to recursively sort. Or it wants to somehow finish quickly after this using recursion. And so it picks this element x and says, what I want to do is split the array into 3 parts. I want the part that contains stuff that's less than x. I want the part that contains stuff that equals x. And I want the part that contains stuff that is bigger than x. Okay? All right. So if we look at what this doesn't sort yet. So A equals range, I don't know, let's say 12, import, let's say. shuffle. Okay, so there's our array A that we want to sort. And if we call this function, let's see what it does. It picks an element, a random element. Maybe we should, well, we can maybe guess what that random element was here. In this case, I think it was probably 2. And then it splits the array into the stuff that's smaller than 2, and then the stuff that's bigger than 2, and then the stuff that's equal to 2, and puts those together. We can try it again. In this case, 1, 2, 3, 4, 5, 9. I think the element x that it picked here was probably 9. There's the stuff that's bigger than 9. There's the stuff that's equal to 9, and there's the stuff that's smaller than 9. And maybe we can guess the pivot here as well. Here I would guess that this element x, which is called the pivot, was 4. So this doesn't sort yet. All it does is split into the stuff that's smaller than the pivot, stuff that's equal to the pivot, and stuff that's bigger than the pivot. So to get it sorted, what's left to do? So here's the pivot 4. Stuff before 4 is not sorted. The stuff after 4 is not sorted. Is 4 in the right place? Yep. It's definitely in the right place because everything smaller than 4 comes before it. Everything bigger than 4 comes after it. So it's always in the right place. In this case, 2 is in the right place. 5 is in the right place here. It's just that this stuff is not sorted yet. And this stuff is not sorted yet. So all we have to do is sort that first part. And sort that second or the third part. Okay. Okay, so that's it. The recursive, the famous quicksort algorithm is really only a few lines of code. You pick a random pivot, you partition into the stuff that's smaller than, the stuff that's bigger than, and the stuff that's equal, and you recursively sort the stuff that's smaller than, and you also recursively sort the stuff that's bigger than, and then you're done. Yep.
Intuitively, when we were doing that game, I guess, earlier on in the first couple lessons, we were trying to pick a number that was random.
Yep.
Intuitively, you kind of hit towards the middle, and then you break it down
Yep.
quicker. Now, why random any number in this sort?
Well, because we don't have a good idea. What we would really like is to pick the number that's right in the middle. But, you know, if we want the number that's right in the middle in sorted order, well, we don't have, so here's what we would like, is someone to give us the numbers in sorted order, and then we would pick the one in the middle and say partition around that. Problem is, what we're trying to figure out is the sorted order, so we don't have a good idea which number is going to be right in the middle. We don't have a good idea of the median, and so picking a random one is as good as anything else. And in fact, in a second year course, you'll analyze this carefully and see that it's almost as good as knowing the exact median. Okay. So any questions about quicksort? No. So that's your first real famous algorithm.
Is that, when you come to sort there, is that what the method is?
Different, depends exactly how the underlying language library implements it. So in some languages like C, the sorting method is called qsort, and it does a variant of quicksort in most implementations. Okay. One thing I quickly want to show you that we'll come back to next class is something called the power set. So return the list of all subsets of A. So I give you a list of elements like this, 0 through 11, and I want to return every possible subset of those elements. So that means I would like to return the empty set, I would like to return the set that contains only 0, the set that contains only 1, the set that contains only 2, the set that contains 0 and 1, the set that contains 0 and 2, big, giant, every possible subset of these things. And there's a reason you want to do that, and that's that, well, a lot of problems involve looking for a solution which is a subset of something, and so if you just list out all the subsets, well, that's one way to find the one you're looking for. And we'll see that probably next class. But here's a quick way to do it. So if there's nothing in A, then all I'll return is a list that contains one thing, and that's the empty set, nothing. So the list that has nothing. Otherwise, I'll return the power set of A, everything except the first element, and then I'll return that power set plus, let's say, x, how do I want to write this? A at 0 plus x for x and s. So I want to return, so I compute all of the subsets of everything that does not include the first element. And now, well, there's two kinds of subsets. There's the ones that include the first element and the ones that don't. So this gives me all the ones that don't include the first element, and this gives me all the ones that do include the first element. Let's just quickly look at some sample output of that. 1, 2, 3. What did I do wrong? The first line? Ah, yeah, good. If the length of A is 0. Okay, so this gives me all the subsets of 1, 2, and 3. The subset that contains nothing, the subset that contains only 3, only 2, both 2 and 3, only 1, both 1 and 3, both 1 and 2, and finally all of 1, 2, and 3. So a quick question for you. How many elements are in this list here? How many subsets are there? No, not length of A factorial. So if you count this one, you'll see that there's 8. So think about why there's 8 in this example.